Students, it's Nazia Begum here, your physics lecturer, welcoming you all in today's lecture. So, today we are going to discuss uh, chapter 14. Here it is written chapter 9, but actually it is our last chapter, which is chapter 14, electronic devices. Okay, so this is our last chapter. Okay, after this, we are going to start our doubt sessions. So, every day I will tell you which chapter or which unit you have to study, and you study that, and according to that, when I will take the live class, I will ask you some questions related to that chapters, and you can also clear whatever doubts you are having, and we will also solve the numerical problems. Okay, so after this we will start doubt session classes, that will also be your revision classes. Okay, so now let's start this topic, electronic devices. So first of all, let's read its introduction. Okay, for electronic devices, electron plays a very important role. Okay, here in the whole chapter we are going to discuss about the behavior of electron inside any solid material, and according to that, that solid material will be used in different devices as insulator, conductor, semiconductor, etc. Okay, and everything whatever type of material we are basically going to discuss about the electron in that material. Okay, so electron was discovered in 1897 by J.J. Thomson. Its characteristic features, namely its charge, mass, and specific charge. Specific charge is the charge to mass ratio, E upon m. Okay, they all discovered later. It was found that an electron was an essential constituent of the atom. It is an extremely light particle, but because of its different characteristics, it is very important particle. Okay, in fact, their use had led to great technological advancements, due to which the world has become a global village. So whatever technology we achieved till now, that is because of the properties of electrons. Okay, all the devices, all the technology, that is totally, basically, if we go to its root, they are based on electrons. Okay, an electronic device works on the controlled flow of electron through it. These devices are the basic building blocks of all electronic circuit. Whatever electronic circuits we are having, in them we are using these devices. Okay, the branch of modern physics which deals with the study of electronic devices used to produce desired effect is called electronics. Before the discovery of transistor in 1948, the electronic devices were mostly vacuum tubes. Okay, some examples are given here. A vacuum diode had two electrodes, namely cathode and anode, enclosed in an evacuated glass bulb. A triode had three electrodes, cathode, anode, and a control grid. A tetrode and pentrode have 4 and 5 electrodes respectively. In these vacuum tubes, the electrons are supplied by the heated cathode, and the flow of these electrons are controlled by varying the voltage between its different electrodes. Since the electrons can flow only from the cathode to anode, that is from negative to positive charge, in these devices they are also known as valves. Okay, the vacuum tube devices are bulky, operated generally at high voltage, and consume high power. So these were some disadvantages of that tubes. Okay, their size were very high, they were very bulky, their operation was complicated, and they consume very high power. So that's why they are not they were not so much popular. Scientists were always trying to find out the alternative vacuum tubes, and with bulkiness and high power consumption, they are also having low reliability and limited life. Okay, then experimental studies revealed that some solid state semiconductors and their junctions. Now what are semiconductor what are junction, that we will discuss in this chapter only. Okay, so study reveals that some solid state semiconductors and their junctions can control the number and the direction of flow of charge carriers through them. Okay, so by assuming this only, the semiconductor devices are being used. The semiconductor devices are very small in size, they operate at low voltages and consume very low power. They have long life and high reliability. Okay, so whatever defects, or what we can say, whatever flaws the vacuum tube was having, the semiconductor device can cure all of them. Okay, it is a best option. Elemental semiconductors, gallium and silicon, are used for fabricating the modern solid state electronic devices like junction diode, transistor, and integrated circuits. Okay, in this chapter we will discuss the basic concepts of semiconductor and discuss the working and application of such semiconductor devices. First of all, let's see classification of solids on the basis of their resistivity. Resistivity is denoted by rho and conductivity is denoted by sigma. So on the basis of their resistivity or conductivity, the solids are basically divided into three categories: metals, insulator, and semiconductor. Metals have low resistivity and high conductivity. Okay, the value of rho resistivity here is 10 to the power minus 2 to 10 to the power minus 8 ohm meter. This is the range of resistivity. Conductivity is just opposite to resistivity. So conductivity sigma equals to 10 to the power 2 to 10 to the power 8 unit. Okay, then we have insulator. They have high resistivity or low conductivity. So here you can see in metal the resistivity is very low, so its power is in negative. But here in insulator the resistivity is very high, that's why its power is positive, and conductivity is low, that's why its power is negative here. Okay, so you just have to remember the power for resistivity. Conductivity is also having the same power, but only the signs will change. In metals, resistivity is having negative sign, but in insulator the conductivity is having the negative sign. One more thing you can see, that metals are having a conductivity from 10 to the power 2 to 10 to the power 8 unit. Insulator are having 10 to the power minus 11 to minus 19 unit. Okay, in semiconductor they fill the gap in between, so they have resistivity and conductivity between the metal and the insulator. Okay, between metal and insulator there is a gap of conductivity and resistivity. In that gap they come what? Semiconductor. So they have resistivity and conductivity in between the metals and the insulator. So here we can see the resistivity is 10 to the power minus 5 to 10 to the power 6 plus 6. Okay, this is the resistivity. So what will be the conductivity? Conductivity will be having the same power, only the signs will change. So conductivity is having 10 to the power 5 to 10 to the power minus 6 unit, that much range. Apart from elemental semiconductor, certain compound also behaves as semiconductor. Okay, so when we say elemental semiconductor, that means we are talking about one particular material like gallium, silicon. Okay, they individually work like semiconductors, but some materials are there which individually does not work like semiconductor, but when they are mixed with other materials, okay, when we make compound of them, that time they behave like semiconductor. So some example of compound semiconductors are given here, and they are also categorized in certain ways. Okay, so first category is inorganic compound. In inorganic compound we have cadmium, sulfur, CDS, then CDSE, then gallium arsenide, then IN and P. Okay, these are when mixed in a particular ratio they behave like a semiconductor. Then we have organic compounds. Okay, in organic compounds we have anthracene, doped phthalocyanines. Okay, these are the semiconductor. Then organic polymers we are having polypyrrole, polyaniline, polythiophene. These are the organic semiconductors. Most of the modern semiconductor devices are based on the elemental semiconductors and compound inorganic semiconductors. The first category one. Okay, either they are single materials or they are compound. These compounds. We are generally not using organic or compound or organic polymers. We are using inorganic compounds. Development of a few semiconductor devices using organic semiconductors and semiconducting polymers have opened the doors of new technology of polymer and molecular electronics. Okay, so nowadays so many research is going on polymer and molecular electronics as well. Now let us talk about energy bands in solid. Energy bands, they play a very vital and important role in the study of semiconductors, because when we are studying any device which is working uh, on their semiconductor behavior, okay, which is made up of semiconductor, energy band plays very important role here. So according to Bohr's atomic model, the electron in an atom revolve around the nucleus in different energy levels, okay, in different orbits according to the energy levels. Okay, and we have also discussed that the orbits which are having a particular amount of energy, that orbits are only allowed. Okay, discrete energies are there which determined by quantum mechanical laws. Therefore, the electrons have well-defined energy levels in an isolated atom. Okay, an electron can only uh, be in an orbit which is having a particular energy. When two similar atoms come closer, the motion of their valence electrons get influenced due to the electric field produced by the two atoms. This interaction results in splitting of each single energy level into two levels close together by one higher and the other lower than the corresponding level of isolated atom. Are you understanding this? Every isolated atom is having certain discrete energy levels, but when another atom come close to that, the energy levels get disturbed and they split in different energy levels, where we are having lower levels and higher levels. In a crystal, there are very large number of closely packed atoms. Thus, each atom in a crystal is surrounded by a large number of atoms. Hence, a very large number of energy levels are created after the splitting. Are you understanding this? In a crystal, atoms are very close to each other. So, because of presence of so many atoms around one atom, and they are present very close to each other, the energy level is splitted into various numbers. Okay, due to the interaction between various atoms. These new energy levels are discrete but are so close to each other that they appear as a continuous energy variation. So here we can see one figure in which it is shown very clearly that how the presence of atom affect the energy level. So here in the first diagram, here in this first one, we can see isolated atoms energy level. Okay, n equals to 1, 2 and 3. 3 levels we are having. Then if another atom is present near this isolated atom, so here you can see this third level is splitted up into two parts. Okay, the higher energy level has splitted up. Then in a crystal, atoms are so close to each other, so here you can see that this third energy level has splitted in so many parts. Okay, so here you can compare that what happened with the energy level when the atom is isolated, when two atoms are present close to each other, and when many atoms are present close to each other. Okay, this set of closely spaced permitted discrete energy level is called the energy band. Okay, so here when this energy level has splitted up, okay, it is called energy band now. And one thing very clearly you can see here, that this splitting of energy level is not there in inner shells. Okay, it is there for n equals to 3, that means the outer shell only, not for first or second level. In order to understand the modification of the energy level, consider a single silicon crystal having n atoms. A silicon has 14 electrons. The electronic configuration of silicon is 1s2, 2s2, 2p6, 3s2, 3p2. From Aufbau and Pauli's principle in chemistry, I know that I hope that you all understood the electronic configuration, okay, in SPDF uh, orbits, etc. Okay, so from there only we got this configuration of silicon as 1s2, 2s2, 2p6, 3s2, 3p2. The energy level of electron in an isolated silicon atom are shown in figure 9.01. So this is the energy level diagram for silicon only. And in that, the outermost orbit is having 4 electrons, okay, 2 electrons in 3s, 2 electron in 3p subshell. Subshell 3p, however, can accommodate 6 electrons. In each silicon atom, there are 2 quantum states in energy level 1s, 2 quantum state in energy level 2s, and 6 quantum states in energy level 2p. You know that this, na? In S, 2 places are there, in P, 6. Okay? 2 quantum states in 3s energy level and 2 quantum state in 3p energy level. Hence, out of 4n valence electron in the crystal, 3p energy level has 2n states filled and 4n states empty. In other words, 4n valence electrons. There are 8n available energy states. These 8n energy states can either form a continuous band or they may group in different bands depending upon the distance between the atoms. Then let's discuss about formation of energy band. Let the atoms initially be far apart so that there is no interaction between them. The distance between them is gradually reduced till it becomes equal to the actual inner atomic spacing between the silicon atom. Okay, let us see what happens as the inner atomic separation decreases. So here in the x-axis we have taken inner atomic separation, in y-axis we have taken energy. Okay, so as the separation decreases, you can see what happened to energy. We are having two bands, valence band and conduction band. Valence band is that band in which valence electron exists. Conduction band is that band in which conduction electrons exist. They live there. Okay. So first what happened when R equals to R3? The interatomic separation is very large. So there is no interaction between the atoms. Okay. So there is no interaction between the energy levels as well. When R is between R1 and R2, okay, here between R and R2, that means here in this place, okay. So here what happened? R is greater than A when a separation is less than that in case. In this situation, the interaction between the valence electrons of the atom becomes appreciable, okay. Here you can see the valence electrons are involved with each other. The single 3s and 3p energy level start splitting into large numbers. When R becomes equals to R1, which is greater than A, that is separation is less than that in case 2. So that time what happened? uh, the valence band, they not only come close to each other, but they start overlapping and get mixed with each other. Okay, in this situation all the 8 and levels get continuously disturbed and form a single energy band. At this stage it is no longer possible to distinguish between 3s and 3p electrons. One can only say that 4n levels are filled and remaining 4n levels are empty. Okay, but we cannot distinguish between 3s and 3p. When r equals to a, that is separation becomes equal to the equilibrium separation. So that time what happened? The filled and unfilled bands get separated from each other by an energy gap called forbidden gap, and two levels are formed here. First is valence band and second is conduction band. So here when the separation between the atom becomes equal to the equilibrium separation, so that time what happened? In an atom clearly two bands appeared. One is valence band, second is conduction band. Between valence band and conduction band there is forbidden gap. Forbidden means not allowed. So here in this forbidden gap, okay, whatever area this forbidden gap is having, in this gap no electron, uh, in this gap here no electron is allowed. Okay, in forbidden gap no electron can live. They only can live either in valence band or in conduction band. Okay, electron generally in normal situation, in normal condition, they exist here in valence band, and when they get energy they jump to the conduction band. Okay, so here today we have discussed some basic things about energy bands. Now in next lecture we will discuss in more advanced manner. Till then, goodbye, take care, do some productive work, and the most important thing, be healthy, be safe.